Okay, so here's the first question. It says, is KOH an acid or a base? So anytime you think about a base, right, especially if in this case you have KOH, right? So by definition, if it's an acid, right, you need to really have that presence of a proton, right? If it's a base, typically I tell my students that if you're looking for a strong base, you would have your first group, right, and your second group, right? Sorry, group one and group two, right, which is your alkali and alkali earth metals. And then basically, if you have a hydroxide ion, in this case, it's OH, right, that means it would turn it into a strong base, right? So maybe let's check what they've written out. So they're saying in chemistry, an acid is a chemical substance that donates a proton or hydrogen ions. This is right because the reason why it's an acid, right? But by Arrhenius, if you haven't heard of him. So what Arrhenius said was for a substance to become an acid, you need to be able to protonate or donate that proton, right? And right, if you have there is usually a bonded hydrogen atom in the acid that can be converted to a cation or anion in water. Okay, so let's just quickly go over this. The acidity of the acid depends upon the number of hydrogen atoms released by the acid. The more the number of hydrogen atoms released, the higher will be the acidity of the acid, and the pH of the solution will be less. For example, acetic acid, sulfuric acid, etc. Okay, so I wanted to word this a little bit differently. I think it's just easier for you to remember at this point. What they're saying here is they're comparing acidity, right? So, say for example, if you're looking at sulfuric acid. So we know that sulfuric acid, H2SO4, is a very strong acid, right? It's part of your seven strong acids versus acetic acid, which is a weak acid, right? So the reason why sulfuric acid is actually very acidic as opposed to acetic acid is because sulfuric acid is in terms of the number of protons, right, it can actually release, right, it actually dissociates completely, right? If you write down the equation H2SO4, right, it's going to dissociate its protons quickly, right? And on the other hand, if you have acetic acid, right, which is a weak acid, so acetic acid is CH3COOH, right? And fun fact, acetic acid is actually found in vinegar, right? So in that case, the reason why it's a weak acid is because you have this solubility constant, right? So it's not going to dissociate its protons completely. That's why it's a weak acid, right? And depending on your solubility constant, which is K, right? So in this case, because it's an acid, it's Ka. Then that means if you have a greater Ka, right? What would happen to your acid versus if you have a lower Ka, right? So we know that if you have a greater Ka, that means it's easier for the acid to completely dissociate. Does that make sense? That's why it makes it a stronger acid. Okay, great. So that's about it. And the same thing really applies for KB, right? Which is the counterpart, right, for the base. Right, so they're talking about KOH here and it's going to dissociate. As you can see, so they have KOH and water, right? So in the presence of water, it's going to dissociate completely. And because you have this aqueous, right? So what they're saying here, maybe we can just elaborate on that. So we know that you have KOH, right? So in the presence of water, what happens to this base is it's going to dissociate completely into K plus, and that's why you have only the forward reaction arrow plus OH minus, right? And this is going to be aqueous, right? Because they're ions, right? So it's aqueous environment, and this is also be aqueous. Okay, great. So yeah, we typically don't write water here. The reason why is because you don't really have solubility. So if it's in an equilibrium reaction, right? Remember Bronsted-Lowry and bases, right? That means if we look at acetic acid, on the other hand, we have CH3, COOH, right? This is acetic acid. And if this is combined, right, in the presence of water, you're going to have your equilibrium reaction where it's going to dissociate, but it's not completely. And this is instead, right, because we know that CH3COOH is an acid, right? That means it's going to donate its proton to water, right? And you would result to CH3COO minus, right? Because you're losing that proton. And this would become, let's see, H3O plus, right? Because water is going to gain that extra proton, therefore becoming H3O plus. And this is also aqueous, right? And this is also aqueous. And on top of that, because we know that the CH3COOH is an acid, right? Based on Bronsted-Lowry, right? What did they say? So they're saying that you have an acid, you have a base, right? Because you have an acid, right, you're going to have that counterpart, which is your conjugate base, right? And this is your conjugate base, so C base. And then your conjugate acid is H3O plus. Does that make sense? So yeah, there's going to be a couple of scientists that you have to remember. So first, it's Lewis. Actually, Arrhenius is the first one. And then you have Bronsted-Lowry. Then the next one would be Lewis, right? So for Lewis, it's just basically the way you're going to transfer your electrons in that sense. Okay, so these are the pioneers in science who made chemistry interesting. Okay, great. So let's go back. Okay, so because we're on the same topic, right? They're talking about calcium hydroxide, right? So we know that it's CaOH2, right? So the reason why it's a strong base, again, because if you remember, right, for Ca, maybe we can have my periodic table opened. So let's share a periodic table. Okay, can you guys see my periodic table so far? Okay, great. So if you remember, right, you have your alkali metals and your alkaline earth, right? That's basically group 1 right here and group 2, right? So calcium is found in group 2, right? So as a result, it's part of your alkaline earth metals. And remember what I said about strong bases, right? If you have alkali metals and alkaline earth metals combined with a hydroxide anion, which is OH minus, then therefore it becomes a strong base, right? So we know that CaOH2, calcium hydroxide, is a strong base. Great.